Hello everyone and welcome to this video. This is a solved example. It's pretty important and I wanted to record a video for you going through the steps step by step. Um, this is the plastic analysis of continuous beams. Let's take a look at this example. We have three spans. Each span has different loading, and I want you to pay very close attention. Each span has different M plastic, and I talked about this before. So each span has its own strength. Span AB is double the capacity of span EG. And luckily, we were given in this example the magnitude of M plastic. So we know that M plastic is 30 kilonewton meter. Okay, so what are we being asked to do? We're asked to find, this is point A, we need to find the position of possible plastic hinges to form collapse. And the second thing is we need to find the load factor that will cause collapse using the static method. And the third part of the question is to draw or sketch the final bending moment diagram at collapse. The last one is the easiest. So even though it's the last one, don't forget to answer this question. How do we start? What's the first step? We need to evaluate each span separately. So let's go with point A. Where are the possible plastic hinges? Let's start with joint A. Is joint A fixed support or a pin support? If it was fixed, then there would be a potential plastic hinge at A. But because it's a pin, there is no possible plastic hinge at A. Okay, what about the intermediate supports? Point B, point E, those are the intermediate supports. Is there a possibility for a plastic hinge at the intermediate supports? Yes, absolutely. So I'm going to go ahead and put the red dot. These are possible plastic hinges. Can there be a plastic hinge at G? No, because G is a hinge support. The moment at G will always be 0. It cannot be M plastic. All right. Is there any other positions that can have a plastic moment? Yes. At the spans, within the span, there's going to be a plastic hinge. Any guess where the plastic span will be for part AB? You can guess it's going to be in the midspan, but I've solved this in the lecture. It's not exactly in the midspan. It goes towards A, slightly towards A, like 10% of the span towards A. So for the sake of time and accepted approximation, we can assume it's in the midspan. We will get close enough answer. What about EG? EG, we will definitely have a plastic hinge under the support because this is going to have the positive bending moment, the maximum positive bending moment. What about span BE? B, C, D, E. We're going to have one plastic support between B and E. The reason is, if we take this beam outside, we can represent it as a fixed beam with 2 points, with 2-point loads. So how many plastic hinges are required to form a collapse mechanism? We agreed that we will need 3. 1 at the fixed, 1 at the other fixed, and either under this load or the other load. So which one is going to be? If it's obvious, we can guess. But in this case, it's difficult to guess. So you know what? We'll solve it twice. We will assume that it's at point D first, and then we'll assume it's at point C, and judge whether we're trying to calculate M plastic or whether we are trying to calculate the load factor. If we are looking for M plastic, we solve all the spans and we choose the maximum. If we are solving for the load factor lambda, we evaluate all the spans and then we use the minimum, the smallest load factor. Okay, so I mentioned that probably the part C is going to be the easiest. So let's go ahead and guess what the final bending moment at collapse is, and it will help us confirm that part A is correct. Let's go ahead and clear some space. I'm going to plot the diagram here at the bottom. Let's put a copy of the beam in black. Point A is a pin support, no problem there. Point B is continuous, point E is continuous, and the end G is pin. What is going to be the bending moment at B? We know that there's going to be a plastic hinge at B. So at collapse, when the plastic hinges are forming, what is the moment at B? Is it going to be 2 M plastic or 1.5 M plastic? I mentioned this before. At intermediate supports, we need to take the smallest M plastic because this value will be reached first. So the moment at B is going to be 1.5 M plastic. So we know that this is going to be the moment at B. What about the moment at E? Is it going to be 0.5, 1.5 M plastic, or just M plastic? We'll take the smaller. This is why this is going to be M plastic. Okay, what about the moment at A? The moment at A will always be 0. The moment at G will always be 0. Okay, can we predict the shape of the bending moment diagram for span AB, the very left span? Yes, it's actually very easy, and I have mentioned this many times. If you want to plot the bending moment diagram within the span, look at the moments at both ends, at A and at B. At A is 0, at B is 1.5 M plastic. So I'm going to connect them with a dotted line. And from that dotted line, I'm going to hang the shape of the simple moment version of that loading. So if there was a simple beam here with a distributed load on it, what would be the shape of the bending moment? You probably guessed it right. W L squared over 8. So I'm going to do the same thing, but I'm going to assume the simple beam is the dotted line. So there you go. It's going to look something like that. And here is the trick. From the maximum positive at mid-span all the way to the dotted line is also going to be W L squared over 8. And this is the static method. We're going to use this to calculate the static method. So the bending moment diagram is everything below the black line and everything above the black line, but the math will be calculated from the distance I pointed out. Okay, so can we predict the maximum bending moment in positive at collapse? Remember, this is a plastic analysis problem. So when we keep on loading the beam till failure, can you guess what will the maximum positive bending moment below the beam will be? Yes, it will be 2m plastic. Why is that? Because this is the capacity of the beam. This is the capacity of the beam. I got this from the given load. What's the shape of the bending moment between B and E? Well, let's do the same exercise. If it was simply supported, the point load here is bigger than the one on the right. So I will have a shape that looks probably something like that. This value is bigger than this value. So I'll do the same thing. I'll connect the dotted line, and from the dotted line, I will hang the simple supported bending moment shape. So it will most probably look something like this. Everything above the black is the negative, everything below the black is the positive. So sometimes we can guess where the maximum will be, and sometimes we can't. In this case, it's difficult to tell because the loads are not equal. If they were equal, then I will go by which side is bigger. There is a side that is 1 m plastic and the other side is 1.5 m plastic. So the line is kind of tilted, and then I can guess this way. Here it's difficult to guess because one load is opposing the negative shape. So as I said, we'll evaluate it twice. No problem there. What's the shape of the bending moment for span EC? I will connect the dotted line and I will hang the shape of the simple bending moment diagram of this beam, which will be a point load like that. Everything above the black line is negative, everything below it is positive, and I know that the positive plastic hinge will be at the peak maximum bending moment, which is going to be most probably under the point load. So what will be the magnitude of moment here? It's going to be M plastic. And why is that? Because this span has the capacity of M plastic. Okay, so if we move forward, we need to calculate the load factor lambda from each span. and that will be the answer for part B. How do we evaluate using the static method, span AB? Okay, first we are going to need to know the simple beam version. The simple beam version will have a bending moment that is W L squared over 8. Can we calculate that for this beam? Yes. This is going to equal 10 lambda. The whole span is 6 squared divided by 8. So that's just the simple beam version. But this beam is not simply supported. We mentioned that at this side, I'm going to take the smaller of 1.5 M plastic and 2 M plastic. So this is going to be 1.5 M plastic. So I got it here. What is going to be the shape of the bending moment diagram? I'm going to plot the beam. There is 1.5 M plastic here. There is 0 moment here. I'm going to connect the two using the dotted line, and I'm going to put that bending moment from the dotted line. It will look something like this. As I said, as an approximation, we will assume that this distance x is going to, in the midspan, is going to be 3 meters. This is going to give us an accurate enough result. So, what is going to be the magnitude of the moment at the maximum bending moment? In the previous slide, we realized that the plastic hinge will happen at 2 M plastic. Now, if we want to figure out how much is lambda, we're going to have to use the static method. What is the static method? Here it comes. Look, what is this distance? This distance is 2 M plastic. All right. What is the distance from the dotted line to the beam? What is this distance? Look, there is a ratio between this value, which we're looking for, and the base of the triangle. It's going to be half the base. Therefore, this part is going to be 0.75 M plastic. It's half the base. All right. So what is the overall distance? We got this from the simple version, from the simple bending moment version. So this is the static method. I'm going to say 2M plastic plus 0.75 M plastic. This has to equal 10 lambda 6 squared divided by 8. Do we know M plastic? Yes, M plastic is 30. It was given. Okay, so what's going to be the only unknown here? The only unknown is lambda. If we go solve for lambda, we will realize that lambda is 1.83. What's the unit of lambda? It's unitless. It's a load factor. This is the load factor that will cause collapse. We're going to repeat this process for all three spans. I'll go through it at a faster pace now, and then we will pick the minimum lambda. Let's evaluate span BE. First, we will assume that the plastic hinge is at C. Then we will figure out lambda, and we'll solve it again, assuming that the plastic hinge is at D, solving for lambda, and then we'll take the smallest. All right. What is the bending moment diagram if BE was simply supported? It will probably look something like that. So why is this distance bigger? Because this load is bigger. Can we figure out for the simple beam BD? Do we know how much is this bending moment? If the load here is 30 lambda and this is 15 lambda? Yes, this is going to be a simply supported beam. So by taking summation of moments at B equal 0, we can figure out the reaction at D. So the reaction at D, if we do the math, it will turn out to be 20 lambda. Is there a way to get the moment at B, or the reaction at B? Yes, it will turn out to be all the forces up in positive y minus all the forces in negative y. It will have to equal 0. So the reaction here is going to be 25 lambda. So how do we get the bending moment at point D and at point C? I think this is not point D, this is point E. And that will make this point D and this point C. Okay, this will result in the moment at D is going to be 20 times the distance 2. So this is going to be 40 lambda, and at C it's going to be 25 times 2, and that will be 50 lambda. All right, so we know that if we connect the dotted line and put the shape of the simple beam, we will get the bending moment at collapse. What is going to be the bending moment at collapse for point B? I'm going to take the smaller of these two values, so we take 1.5. At joint E, right of joint E, the beam has a bending capacity of 1 M plastic. Left of joint E is 1.5 M plastic. So which will fail first? 1 M plastic will fail first. Excellent. All right. So if we assume that the maximum bending moment is at C, what would be the bending moment at collapse? It's going to be the capacity of the beam, M plastic. All right. So this distance is M plastic. Is there a way we can get this distance? Yes, by similar triangles. I'm going to divide this. Um, I'm going to isolate the parallelogram into a rectangle and triangle. And I'm going to do the similar triangles to figure out the overall distance. So when we do the math, we'll realize that the distance from the beam to the dotted line at C is 1.3 m plastic, and from the beam to the positive maximum is 1.5 m plastic. So when we add 1.3 m plastic plus 1.5 m plastic, this is going to be the entire distance. So how much is this entire distance? It's the value we got from the positive bending moment. So this will have to equal 50 lambda. Because we know m plastic is 30, the only unknown is lambda, and this will result in lambda being 1.7. So far this is the minimum. The other one was 1.8 something. This is 1.7. Let's double check that C is the plastic hinge. We will have to go and solve the same span, but assuming that the plastic hinge is at D. We'll have to do the same thing at point D. We will assume that the plastic hinge is at D. I will recreate the simple bending moment diagram, which we got in the previous slide. And we realize that this magnitude was 40 lambda. And this magnitude was 50 lambda. Now, we need to figure out how much is the distance from the dotted line to the beam. If we do the similar triangles, we will realize it's 1.17 m plastic. Okay, now all what's left is the entire distance will have to equal the simple bending moment diagram at point D. So if we do the math, 1.17 m plastic plus, that's the top part to the black line. Now from we add the bottom line, 1.5 m plastic. This has to equal 40 m plastic, 40 lambda, which is the load factor. Because we know the m plastic is 30, it was given. That means that the only unknown is lambda, and in this case, lambda is going to equal 2. So 2 is not the minimum. 1.7, lambda 1.7 is still the governing case. Now, the last span, span EG. because the simple the simple bending version of this beam is going to be a triangle like this. If this was a simple beam with a point load on it, we can guess how much is this maximum bending moment. Can you guess? It's PL over 4. PL over 4. So in this case, P is 20 lambda, L is 4 meters, and we're going to divide that by 4. So eventually it's going to be equal 20 lambda. So we agreed that the moment at E is going to be 1 m plastic. That's the negative. The drill is you connect the negative to the opposite side, which is going to be 0. The moment at joint G is 0. And then we're going to have to figure out the entire distance at the point load. What is the little distance here? It's going to be half the base. In that big triangle, in the negative triangle, the short distance between this beam and the dotted line at midspan is going to be half M plastic, half the base. So when we add half M plastic on top to the M plastic at the bottom, it should equal PL over 4. So let's do that math. 0.5 M plastic plus 1 M plastic. This has to equal PL over 4. So it's going to be that magnitude, which is 20 lambda. We know that M plastic is 30, so we figured out those sides. The only remaining unknown is lambda. And when we do the math, we will get that lambda is 2.25. That's not the minimum. So we will go revisit each span and pick the minimum lambda. And in this case, the critical load factor that will cause collapse is 1.7. I'm also going to add a PDF summary of this and make sure to go through this example. You can solve it correctly and then let me know if you have any questions. That's everything, and see you.